Every day throughout Germany, thousands of trains operate through a complex network of railway lines. From the well-known high-speed ICE trains to the local passenger trains and freight trains, they run dependably on time. Individual routes can have hundreds of trains per day. Stations and terminals on converging routes can have over 1,000 trains per day. These trains, in their range of different speeds and stopping patterns, must share the same railway network without interfering with each other. This is all accomplished while adhering to rigid traffic control safety procedures. The engineer of each train is issued a detailed schedule that specifies arriving and leaving or passing times for each station on the route. The schedule is much more than a list of times. The schedule must be achievable in normal service, or the service will not be dependable. An achievable schedule requires careful consideration of every predictable event, including the interaction with other trains. The characteristics of the locomotive, the cars, the tracks on the route, and the signal and control system must all be considered. From the locomotive engineer's point of view, there is a procession of trains in the opposite direction and a clear track ahead. Sometimes the track ahead is clear because a slower train, like the train of automobiles coming up on the left, has been routed to a siding. This is done at just the right time to avoid delaying the train behind or a train moving in the opposite direction. It is also accomplished with the least possible waiting time for the train routed to the siding. Not visible are the highly skilled schedule planners, train directors, dispatchers, and signal technicians that build and maintain the framework of dependable rail service. They maintain a constant watch over the progress of every train, adjusting the scheduled operation as necessary to maintain reliable service if one train encounters problems.
Zur Regionalbahn nach Holzminden, über Salzgitterbad, Sesenabfahrt, 10:04 Uhr aus Gleis 1.
The platform announcer works closely with the train directors, ensuring that the passengers have accurate information. The train director's view of the traffic may be through the windows of a control tower, the figures in a computer information system, or the display panel of a signal control system. We will watch a train arrive at Braunschweig from the point of view of the locomotive engineer and of the train director. An announcement of the arrival at Braunschweig is made in the train.
Meine Damen und Herren, wir erreichen in wenigen Minuten Braunschweig. Sie werden alle vorgesehenen Anschlusszüge erreichen. Die wichtigsten Reisemöglichkeiten haben wir für Sie im Fahrtplan via Reiseplan zusammengestellt. Wir möchten uns von unseren Fahrgästen, die dort aussteigen, verabschieden und wünschen Ihnen noch einen angenehmen Tag.
Like champion chess players, the train directors make a complete assessment of each action before proceeding. The combined effort of the schedule planners, train directors, dispatchers, signal technicians, and locomotive engineers make events like the arrival of 2 ICE trains at Braunschweig on the hour all day long commonplace. The train has been under the watchful eye of the train directors, but only now becomes visible.
Ja, Effa, hier bitte.
Ja, grüß dich. Ich bin bei dir auf 3 bitte zum Waschen.
3 zum Waschen.
Ja, grüß dich.
The train is about to enter the Braunschweig station. The train director's tower is on the left.
Der müsste vorbei sein, oder? Ach, siehst du nicht. Ja. Ja, Signal 6 ist noch und jetzt wird auch gut. Also kannst du rausgehen. Ja. Ja, alles klar.
And again, the hourly ICE trains arrive on time. Maintaining the safety and reliability of railway operation requires extensive training. Several technical universities in Germany teach railway sciences. The Railway Operations Laboratory of the Friedrich List School of Traffic Studies at the Technical University in Dresden allows sophisticated training in railway operation and signal technology without affecting railway service. The laboratory's railway is recently constructed, but has a 40-year history. The laboratory's railway is a 1/87th scale, or HO, model railway. Distance, however, is represented in 1/200th scale. It accurately represents 105.8 kilometers of railway line. There are 4 routes and 9 traffic control stations. A shadow yard and connecting tracks on the lower level allow trains to exit one end of the system, wait unseen, and then return to the system as another schedule. Unlike a typical model railway, no one directly operates the trains. Trains respond to the students working in the laboratory in the same way that trains respond to traffic control employees on an actual railway. A computer system and specially made interface controls train movements in response to signal indications. The computer system also governs the clocks used for train operation in the laboratory. Trains operate at the correct speed for the signal indications based on the model railway distances and the time from the computer system. The signals are not constructed to the same scale as the rest of the railway. They are intended to be accurate representations of a sufficient size to be observed by the students. Each signal shows the appropriate signal aspect for the route it governs. On the routes equipped with automatic block signals, the signals respond to the block conditions and to the signals in advance. Each of the 9 traffic control stations has a different type of signal control equipment. The control equipment represents all types of operation found in Germany, from the oldest entirely mechanical systems to the most recent solid-state systems. Another specially made computer system interface translates the mechanical action of the older equipment into the electronic input needed for the signal system. This electronic interlocking using a tablet for command entry is the same as that seen here in Braunschweig. This electronic interlocking at Waldhof in the laboratory is similar to the latest equipment found in the new control centers. A new system being developed has a video camera in one of the locomotives and a computer interface allowing direct control to give students a locomotive engineer's eye view of their work. This is a key-type interlocking machine, one of the oldest types of interlocking. The operator removes a key from the machine, walks outside to the switch to be thrown, and uses the key to unlock the switch. Throwing the switch releases a second key. The second key is inserted into the interlocking machine in the appropriate position, which allows the removal of a key that is used to unlock the signal button.
So, yeah, now you have to lock in electrical way.
The block instrument. So for C2,
Yes.
correct?
Okay, that was it. And now you can switch the signal.
Grade crossing signals in Germany are often controlled by the traffic control operators using the same signal control equipment that is used for train movements. The signals must be operating and the crossing must be closed for road traffic before a train can be given a signal to proceed. The laboratory represents this using model crossing signals that operate exactly as their counterparts along the railway line. Sometimes, just as in actual railway operation, the equipment fails and it is necessary to call a signal technician.
Triebwagen. 114er. Der kam aus dem Betriebshof und den stellen wir jetzt bereit in Gleis 1, Richtung Kreuzmingen.
Here at Braunschweig, an entrance-exit, or NX, interlocking machine controls the signal system. A route through a complex track arrangement is set for a train by pushing a button on the diagram where the train will enter and another where the train will exit.
Koblenz über Hannover, Bielefeld, Dortmund, Köln, Abfahrt 9:52 Uhr, Ausgleise 6. Zum Intercity Express Walter Gropius nach Stuttgart über Hildesheim, Göttingen, Kassel.
The interlocking machine at Adorf in the laboratory is an entrance-exit machine similar to the one at Braunschweig.
Start and torch it. And now the signal. Now the first part is free, and I can set in another route for auto train in this part.
German operating rules require markers on the rear of a train. Their presence indicates that the train is complete. In manual block territory, operators must check the markers of each train to ensure that the line is not blocked by an uncoupled portion of the train. Each train on the laboratory railway carries markers on the rear. The markers are a miniature version of those carried on the rear of German railway trains. Traffic on the laboratory railway operates as prescribed by schedules, just as the railways in Germany. Using the same type of scheduling software used in German railway operations, students devise operating plans and schedules that are used in the operation of the laboratory railway. Each control station is equipped with a telephone for reporting train movements among the stations, and the paperwork generally found on the desk of a railway traffic control office. The only difference between laboratory train operation and actual train operation is the size of the trains. This interlocking machine at Magdeburg controls switches and signals electrically. The machine has mechanical conflicting route blocking. The same type of interlocking machine is used at Zellwald in the laboratory. In German practice, even entirely mechanical signal equipment at each station is electrically linked between stations to prevent adjacent operators from lining trains into an occupied track between them. Here at Dornbach, there are two control stations, one for each end of the station. To demonstrate the electric interlocking between adjacent stations and the adherence to railway operating practice that is observed in a laboratory, a train is operated from Zellwald through Dornbach. The operator at Zellwald calls to offer the train. The Dornbach operator must check to ensure that the line is clear and that the train can be accepted. The lever releasing the signal at Zellwald is operated. The electricity that will release the signal lever at Zellwald is generated by operating a crank on the side of the machine. As the train approaches, the procedure of the next station releasing the signal control is repeated by the two control stations at Dornbach. Once the locking has been released, the large levers controlling the switches and signals can be moved. In actual railway operation, steel cables around the drum on the levers would pull on the switch points or semaphore blades. In the laboratory, the computer interface operates them when the lever is moved. Specially made electric motors translate the electronic information back into mechanical action for switch points and semaphore signals. After the train passes the signals, they are restored to the stop position. The operator at the far end of Dornbach must check for markers on the train before releasing the track between Dornbach and Zellwald. The procedure is the same at the close end of Dornbach. The laboratory railway has one feature not found on the German railways. At 2 locations, the laboratory railway crosses a doorway. The track crossing the doorway is constructed on a section of framework that is hinged on one end and rolls open or closed. The 2 doorway bridges are fitted with a warning light and an electric locking system. If a doorway bridge is open, trains will stop. If a train is approaching, the doorway bridge is electrically locked, the warning light is displayed, and the bridge cannot be opened until the train passes. The conclusion of the tour of the laboratory, just as the study conducted in the laboratory, leads to the German railway system.